All right, let's get started with section 6.3, introducing exponential functions. And this will be the last section that's tested on the chapter 14/6 test. So combining the two sections from chapter 14 and the first three from chapter 6. All right, so first objective, let's evaluate some exponential functions. So exponential functions is just a base and a power. You can put these into your calculator. I'm not going to spend time doing these. Try problem 11. Make sure you can get the calculator to do exponential powers of whatever 11 is. But this is old hat. We should be able to do that. All right, just a review here of some law of exponents. If we have a to the s times a to the t, that's the same as a to the s plus t. A to the s, all raised to the t, is the same as a to the s times t. AB to the s is the same as a to the s times b to the s. 1 to anything is 1. A negative means reciprocal, flip it over, and anything to the 0 is 1. Let's look at an exponential growth function. So let's say we have a function where the value doubles every 1 unit increase. And at the beginning we have 5. All right, so this would be the inputs, this would be the output. If we start at 5, after 1 unit, we're at 10. Once we go to 2, we're at 20. When we go to 3, we're at 40. So every increase of 1 doubles what we had before. Here's our function form in, this is the function in exponential form, ca to the x. Now, a is your growth factor, like times by 2 or times by 3. Whatever this number is, a, that's what we're timesing by. And if x is 0, remember anything to the 0 is 1. So 1 times c is just c. C is your initial value, what you have if x is 0. This is also the same as the y-intercept. C is the y-intercept. All right, if we increase by 1, remember we double. So increasing by 1 divided by the original just gets us a, our growth factor. Right? So if we increase by 1, we take our first number and times it by a. All right, so let's take a look at 3 different situations, see if we can figure out if they're linear, exponential, or neither. Let's look at the first one. In between all these numbers, we're subtracting 3. So if we're consistently adding or subtracting the same thing, we are going to be linear. And we know an equation for linear functions, y equals mx plus b, where b is the y-intercept, and m is your slope, -3. So we've got ourselves an equation. If we look at the second one, we're adding 2, then we're adding 3, and we're adding 4. This is neither. You either need to be multiplying or adding by the same amount. So in this case, we're multiplying by 1/2. Here we're timesing by 1/2. And even though we're dividing by 2 for exponential functions, we talk about what we're multiplying by. So dividing by 2 is the same as multiplying by 1/2. So we've got our function, y equals ca to the x. Y equals, c is our value initially when x is 0. So 16, 1/2, the growth factor to the x. Try problem 21. So now can we graph these? So graph the exponential function y equals 2 to the x. So right now, this could be written as 1 times 2 to the x, 2 to the x, where c is 1, so 0, 1 is on the graph, and we know that our a is 2, so we move over 1, we double, 1 turns into 2. We move over 1 more, and 2 doubles to 4. All right, we can plug it into our graphing calculator, y equals 2 to the x, and it would look just like that. Now, a couple important points here. The domain is going to be all real. The range is all positive numbers. We're going left and right forever, but we're going up forever. We have no x-intercepts. The y-intercept is always going to be 1. And the intercept is always going to be c, right? So this graph is for just a to the x, but if you have a c, the intercept will be c. The x-axis, y equals 0, is a horizontal asymptote. A line will never cross. And a is increasing and 1 to 1. So it's always going up. It always has 1 input for every output. And 0, c, 1, a, and negative 1 comma 1 over a will always be on your graph with no corners, gaps. It's always smooth and continuous. Let's talk about going down. It's the same thing. So this will be 0 comma c, 1 comma a half, negative 1 comma 2 are the points always on your graph. All right, so we can see if we plugged both of these in and graph them, notice they both cross at 0 comma 1, but y to the 1/6 is much steeper going down than 1/3. So the rules are the same here, except we're decreasing instead of increasing. All right, now what about transformations? So let's start by saying y equals 2 times 3 to the x, and then we'll worry about the transformations. All right, we know that this is always going to cross at 0 comma 2. Okay, and we go over to 1, and we're going to take our 2, plug it in here, so 0 comma 2. If we go over 1, the y value needs to get times by 3. So 3, 4, 5, 6. So we know that we're up here at 1 comma 6. Remember, if you plugged 1 in here, 3 to the first is 3 times 2 is 6. And we know that negative 1, we're also going to have take 2 and divide it by 3. So negative 1 comma 2/3 will also be on your graph. All right, we know that we have an asymptote. We know we're going to start taking off just like that. That's what it would look like without the transformations. All right, so transformations. All your x's get subtracted by 1. So in this case, we're going to have, instead of, let's make our t-table here. So our 3 points we had before were negative 1 2/3, 0 comma 2, and 1 comma 6. And so in this case, we're going to end up taking our x's and subtracting them by 1. Negative 2, negative 1, and 0. We're going to take all of our y values and go down by 4. So 2/3 minus 4 is negative 3 1/3. 2 minus 4 is negative 2, and 6 minus 4 is 2. And so our new graph, negative 2, 2, 3 1/3 down there, and negative 1, negative 2. And here we have 0 comma 2. Where's the asymptote? The asymptote used to be at y equals 0. Shift that down by 4. Now we're going to have an asymptote at y equals negative 4. And taking off like that. All right, so take your asymptote and shift it by the y transformation. Try problem 37. All right, so now let's talk about, we're going to have this new number e. E is like the number pi, in that it's a very special number that has digits to it. Pi is 3.14159. E is a function, and we'll talk more about this once you get to calculus, but it's the limit as n approaches infinity of 1 plus 1 over n to n. Don't worry too much about what that means for now, but what that means is if we plug in bigger and bigger n numbers, we get a close approximation of what e is. And so we, for our purposes, we'll use 2.718. You'll see the values getting bigger there in the right column. So 2.718 is e. So if we graph that, again, 0 comma 1, 1 comma 2.718. And we use e for a lot of things, just like we use pi for a lot of things. Okay, so we'll talk more about its uses later. If we were to graph this, though, where would it go? All right, our asymptote here stays the same. We're flipped over, and we're crossing here. Normally we would be at 0, negative 1, but because of the 2, we're going to be at 2, negative 1. All right, if we move over 1, we're going to get times by e, so that's 2.718. In this case, it's a negative, so right about there. And as we go to the other side, it's 1 over 2.718, so a little bit less than a half. And there you go. All right, so the points in here would be 1 comma 1 over e. We would have 2. Did I do that right? Yes, we're moved over by 2. So 2 comma 1, and then we'd have 3 comma e. All right, try problem 49, and then we're moving on to solving exponential equations. Here's the key here. If the bases are the same, then you can make the powers equal to each other. In this problem, we don't have equal bases, but we could if we recognize 32 is 2 to the 2, 4, 8, 16, 32, fifth power. Now we get to cancel out the 2's and say 3x minus 1 is equal to 5. 3x is equal to 6, x is equal to 2. Try problem 59. Let's try one more. We need to have the same bases, so it's clear here that e is going to be our base. Can we clean up the right side? So this will be e to the negative 4x, if I'm looking at this, over e to the 3x. E to the 2x minus 1 equals e to the negative 4x minus 3x, right? Because subtraction. Let's cancel those out. 2x minus 1 equals negative 7x. And so now we have negative 1 equals negative 9x. And so 1/9 equals Rx. Okay, let's try one more here. So we have cars coming into Burger King at between the time of 9 and 10 p.m. and they come in at 12 cars per hour. The following formula from stats, which you'll get to senior year if you want to take a statistics class, will be given by this formula. So let's grab our graphing calculator and plug this in. So y equals 1 minus e, and so e on here is right here above the natural log, the ln. So second e to the negative 0.2x, right, for t. And so what's the probability that a car will arrive within 5 minutes? So if t is 5. So let's go to our table. So we'll start with 0 and count by ones. So if x is 5, 63% chance that we're going to show up in the first 5 minutes. All right, how about 30? All right, there's a 99.7% chance that a car will show up in the first 30 minutes, right? So that kind of makes sense. If 12 cars are showing up in an hour, it would be pretty unlikely that all 12 of them show up in the last half hour, right? That's what that's saying. All right, so let's graph it. It's going to look like that. All right, but there really is a restriction here because we can't have negative time here. So let's go into our window and say x is going to be, we'll just say, actually, you know what? Let's leave it as negative 10 and we'll go back into our y and put restrictions on it like we've learned to do. Let's insert a parentheses around our function and say that x has to be greater than or equal to 0. And then let's go and graph it again. All right, there you see it starting to take off. Now we do want a bigger x here because our max x really is 60, right? So let's say 65 here. And we'll graph this. Starting to take off. Now kind of hard to see here because our results are going to be between 0 and 1. And let's just say 2 here. Because we're going to be between 0% and 100%. So you can see really quick, this was the 30-minute mark, right? At 30 minutes, it was like 99% chance that you would get somebody to show up, right? And so what happens as t becomes unbounded in the positive direction? That means as t becomes really, really big, then we get to 1. There's a 100% chance that eventually a car will show up. All right, try problem 101, and then a quick summary there. If you want to graph that down, you can pause the video, but other than that, good luck with those problems. Questions, we'll go over them in class.